Okay, our next speaker is the Professor Yıldıray OZAN. He is from the Middle East Technical University in Ankara. The title of his presentation, Picard groups of the modular space of Riemannian surface with certain finite abelian symmetry groups. Is the professor here?
Yeah. Burcu, I am here.
If you are ready, you can you can share your screen.
Okay. First, I would like to thank you or thank the organizers, Burcu and Murat Hocam, for the conference and for inviting me. And I hope everyone will have a nice and inspiring workshop. I think I may start. Let me try to share my screen. Okay. I will write my talk basically. You may stop me anytime, if there's something you don't understand. I will first talk about some topological preliminaries. Let me write that down. It is basically covering spaces of surfaces by sigma Gn. We will denote oriented surface of genus G with n punctures or marked points. Sometimes we will consider them as marked points, sometimes we will consider them as punctures. So we have something like this, 1, 2, G, and then we have marked points or punctures. Okay, so n punctures here, and we have genus G surface. In particular, sigma 0 is just the two sphere. So if we have sigma 0 n, we mean a sphere with n punctured points or n marked points. And let's denote the set of marked points as beta. So not beta, B. So these are the set of marked points or punctures. And for each I from 1 up to n, let xi be the homology class of the curve which goes around. Okay, so suppose here I have, let me draw this a bit bigger. Okay, this is the two sphere, and we have the marked points and the ith one, the nth one, and the okay, so this is the, let's say, okay, let me try to choose a different color. Okay, so suppose this is the curve xi. I will denote the homology class of this curve by the same letter. Okay, so class and the curve are represented by the same letter. Here, of course, these homology classes, if you sum them up, all of them from 1 to n, they will bound the rest of the surface. If you delete this, curves and the disks bounded by this curves, the remaining surface is bounded by this xi's, sum of xi's. Therefore, this is 0 in homology. Now, let's choose. I'm sorry. Oh, somehow my pen is not working. I think my computer somehow got frozen. Okay. I'm sorry. My classes, and it never, caused a problem like this before, but somehow now it just stopped. I am sorry. Okay, let me try to open another document. Me share screen. Okay. Yeah. Okay. So let me I'm sorry, really sorry for this. Okay, so sigma and g, let me try to explain from here. Sigma and g is an orientable surface of genus G, as I said, and xi's are the homology classes around these punctures. Their sum is 0. And then whenever we have an abelian group, in this case, it will be mostly finite abelian group, but in general, it can be any abelian group. We may define a covering space corresponding to a homomorphism defined from the homology H1 into the abelian group. Of course, it is enough to just define the homology on the generators of the homology group on xi's, so that the image elements also satisfy the relation that their sum is 0. So you just pick elements in the abelian group which generate the abelian group so that their sum is 0. And then you send your generators to those elements in A. That will give you a covering space of the two spheres. And if you have two covering spaces, they are actually equivalent if there is a homeomorphism like this, you know, F tilde from one covering space to the other covering space, which covers a map F, which preserves the set of mark points or branch points. In this case, this will be a branched cover. Okay, let me see if I can. Yeah, my pen is not working at all. Oh, I'm sorry. Okay. I will tell you a theorem of Chen, Haimio Chen, in 2021. He proved the following: if we have the above setup, you know, covering space with finite abelian P group being the deck transformation group. So this is regular cover, meaning that A actually acts as deck transformations of the surface, and the quotient of the surface sigma by A is just the two spheres. Okay, he proved the following: if the base homomorphisms, if the homeomorphisms of the two spheres preserving the branch set B can be lifted, if all such homeomorphisms can be lifted, then this covering has to be something very special in the following way. Either this abelian group is for that fixed prime. Remember, we fixed the prime P at the beginning. Okay, A is a finite P group, abelian P group. So that finite abelian P group either is this group. So you have some exponent of the prime P, and you have n minus copies of that cyclic group, n is the number of punctures, remember. So the rank of the abelian group is just one less than the number of punctures. And the homomorphism which describes the cover maps each xi, the homology class of the loops around xi's, to the generators of the abelian group, standard generators of this, you know, Cartesian product of cyclic abelian groups. This covering is actually is something known. Of course, this is the so-called characteristic cover, and it was known that any homeomorphism of the base lifts to characteristic cover. This is a classical thing. What wasn't known was the third one, actually, first. This is proved in 2017 by Gaswala and Winarsky. They proved the cyclic case. So A, there's the possibility that A can be a cyclic group, but in that case, the order of the group must divide the number of punctures, and each generator is sent to identity element of this a generator of this cyclic group. Okay, and the second case is the high rank case. So this is the cyclic case where the group has rank 1. This is the higher rank case. in that case, the rank of the group is just one less than the number of punctures. So the rank of this group is n minus 1. And here I have n minus 2 copies of p to the power r, zp to the power r, and one copy of zp to the power k. Here k and r are positive integers where k is strictly larger than r, and p to the power k minus r must divide n, and the homomorphism which describes the covering space should map xi's, the generators of the homology, this distinguished generators of homology of the base, to these elements. Here this ei is the ith generator of this p to the zp to the power rn minus 2. Ei means you have zeros everywhere except the ith coordinate, and in the ith coordinate you have 1, and the last coordinate is 1. This is for I from 1 up to n minus 2, and the last generator, which is just the last generator of the homology, is mapped to 0, 1, 0 being the 0 element of this first factor of the group A. Okay, this part is proved by Atalan, Medetoğulları, and me in 2020, in case the prime number is 3, and then Chen generalized this to all primes. This and actually the Gaswala-Winiarski results were kind of surprising results in the following sense. Actually, like sorry, in 1973, Biermann and Hilden wrote a paper which was published in the Annals of Math, and then they made a statement saying that if we have a finite cyclic regular cover of the two sphere, then every homeomorphism lifts. But 45 years later, people realized that that result is actually wrong, and Gaswala and Winiarski corrected it. I mean, they said it is not true, but it is true in this case. So they wrote a paper, and this started the story with the cyclic group, and then we carried this result to rank 2 abelian groups, and the result we obtained was kind of surprising because, you know, here we have this kind of factors. The ranks are not the same, so this is quite different than characteristic covers. And Chen's result, which generalized our result to all primes, it was even more surprising. Even the experts in the field, they thought, you know, something like this cannot be true, but it turned out that this is the case. Okay, so this is the story for covering spaces. So somehow, you know, that theorem describes finite abelian covers of two sphere, branch covers of two spheres, where all homeomorphism of the two spheres preserving the branch set lifts. Now let me talk about algebraic geometric preliminaries, namely the Picard group. Picard group of a surface is basically the set of line bundles, and they form an abelian group. And let me try to explain it, what this Picard group, how you construct it. For that, we may just consider the modular mapping class group of the surface G. What is this? Mapping class groups is the group of all homeomorphisms of the Riemann surface sigma G. And you divide this group by the normal subgroup where the homeomorphisms are isotopic to the identity. So in this group, you consider two homeomorphisms to be the same if one is isotope to the other one. This is known as the mapping class group of the surface sigma G. If you have a finite subgroup of this, there is so-called Nielsen's realization problem, meaning that can you represent this subgroup by really an automorphism, a subgroup of automorphisms of the surface isomorphic to H. So can we find a lifting of this subgroup to homeomorphisms? You see, modular, this mapping class group is a quotient group. And if H is a quotient, subgroup of the quotient group, can we find a group in the actual homeomorphism group whose image under this is equal to H? Can we realize this homeomorphisms, this class of homeomorphisms by really homeomorphisms? This is Nielsen's realization problem. And this is actually true. And the solution provided by Kerckhoff tells us that, and its later generalization, you can realize H as a subgroup of homeomorphisms, and more actually specifically, you can put a complex structure on the surface so that it becomes a Riemann surface. So it's a complex surface, complex curve, or Riemann surface, and H acts as holomorphic maps on this surface. Okay, by MGH, we will denote the moduli space of genus G curves with a group of automorphisms acting topologically like H. So what we mean, we consider all the Riemann surfaces homeomorphic to our surface so that the group H acts topologically like described, by H in the fixed surface here, and the set of all such Riemann surfaces, actually they form another geometric object. It's a quasi-projective orbifold, so it's an algebraic actually variety kind of. There is more detail here. There's another construction using Teichmüller theory. You consider all projective curves C with a subset, so that all these curves with this subset are homeomorphic to our fixed surface, and this set of points are mapped to our branch points. We consider all such curves, and then we divide it by the equivalence relation that, two such surfaces are considered to be the same if there is a homeomorphism which sends one of them to another one, so that the diagram commutes, right? Each curve is homeomorphic to sigma Gn, and if we have two curves like this, if they are homeomorphic, if there's a homeomorphism which sends one of them to other one, then we consider them to be the same. And this quotient again is a model for the moduli space. There is some more actually technical stuff here. Let me skip those since I don't have much time. In 2020, Kevin Kordek proved the following theorem. He proved that if the genus is larger than or equal to 2 and H is a finite abelian group in the mapping class group of a sigma G, the sigma G surface, then by Kerckhoffs's solution and its generalizations, we may put a complex structure on this sigma G surface so that it becomes a Riemann surface, and H acts on that surface as automorphisms of the Riemann surface, so they are holomorphic maps. The result of Kerckhoff is the following. If the quotient of this surface by H is P1, in other words, if it is the Riemann surface, then the Picard group is finite. Here, as I said, Picard group should be considered as the set of line bundles on the Riemann surface, but these line bundles are they are preserved by the action of the finite abelian group H. Okay, so they are kind of equivariant line bundles. It turns out that this Picard group is finite. In general, Picard groups are infinite objects, infinite abelian groups, but in this case, it is finite. And moreover, this finite Picard group is isomorphic to the first homology of the mapping class group. First homology of the mapping class group is nothing but the abelianization of this group, right? If you have a group, its first homology is just abelianization of that group. And here this isomorphism is given by the actually Chern class map. If you have a line bundle, its first Chern class lies in the second cohomology, but universal coefficient theorem tells us that this second cohomology is actually its torsion part is isomorphic to this one, and in this case our group is torsion. Okay, it has another part, but that part actually is not related to our work. So here Kordek described what the Picard group is. And then Kordek also describes how one can compute this homology or Picard group. How can one compute this gadget? And here is some explanation for that. Okay, let me skip all these. They're kind of technical. Okay, it turns out that this homology Picard group is isomorphic to Picard group, maybe not the Picard group, but symmetric mapping class group is isomorphic to mapping class group times H. Here we have semi-direct product, and this is this exact sequence is what? These are the middle one are mapping classes of sigma G of the covering space, but they are symmetric. So S stands for symmetric. These are the ones which are invariant under the action of the deck transformation group. Of course, they since they are symmetric, they descend to the surface below, which is the two-sphere, punctured two-sphere. And if you think it the other way around, each homeomorphism of this sphere lifts, and actually there are h many lifts, okay, and they all these three groups fits into an exact sequence like this. And here the middle one is the semi-direct product of the other two groups. And we are interested in the abelianization of this group, H1 of this one. And it's a standard group theory that if you have a semi-direct product like this, its abelianization is just the abelianization of the first one and then the abelianization of the second one. You have direct product here, but you have this subscript G, meaning that so its meaning is this: you look at the abelianization, but you divide this abelianization by the following subgroup. So you take any element of the G, group G, and you act it on the elements of H by that G, and you look at the difference of the image and H, and this gadgets form a subgroup, and you take the quotient of abelianization by that subgroup. And then if you do the computations, actually, so I will describe the computations for the cases in Chan's theorem for this second case and the first case. Okay, let me. Okay, yeah. So this is the characteristic cover. In this case, H is this group. Of course, it is abelian, so its abelianization is itself. And then here we have the mapping class group. We look at its abelianization and then divide H by this subgroup. And if you do the computations, here G acts on the generators of H as you know, it just permutes actually the generators. So it permutes the punctures, therefore it permutes the homology classes HIs, therefore it permutes the generators of the abelian group, standard generators. So we just divide this H by these differences, basically. And the end result is the following. So this quotient becomes the quotient of the cyclic group by the subgroup generated by N. Of course, that is nothing but the cyclic group Z and of order the greatest common divisor of P to the power E and N. And then here I have the abelianization of the mapping class group. It is well known that the abelianization of this mapping class group is either Z cyclic group of order 2 times n minus 1 in case n is even, or n minus 1 in case n is odd. So this is the result. The Picard group is isomorphic to this finite abelian group depending on n is even or odd. And for this case, which is kind of the surprising case, H was this, and our homomorphism describing the abelian group was this, and H abelianization of H is H, of course. If you compute the quotient here as before, again you get basically the same thing actually. Sorry, yeah, here this computation gives us what? It gives us again the abelianization, sorry, H divided by that subgroup is again the cyclic group. Here we have P to the power K, not P to the power R, but P to the power K, okay? So the second exponent here, not R. All right. And again, the mapping class group part is, of course, the same. So Picard group in this case is just this abelian group. And if you just actually, you know, plug some numbers, for example, if you choose n equals 3, and in that case, since p has to divide n, p can be only 3. So if you have only 3 branch points on the sphere, the only cover you may get in this case is just the abelian group has to be, you know, p group of, and where p is just 3. Okay, no other prime is cannot occur. And if you use standard theory of you know, surfaces, you may compute the genus of the Riemann surface from the Riemann-Hurwitz formula. Basically, you just count the branch points and so on, and it turns out that the Riemann surface has genus tan. So the above results gives us the following: then the Picard group of the moduli space of genus tan curves on which Z3 times Z9 acts in the way that described by the homomorphism phi from homology to the abelian group. That Picard group is Z2 cross Z3. So this is one example. Well, I guess that's all what I would like to say. If I could write, I would give you more detail, but I'm sorry, my pen just stopped working. I think I am done. If there are any questions, I may try to answer.
Thank you very much, Professor Yıldıray Ozan, for your nice presentation and your nice talk. Is there anyone who wants to ask a question or any comments? I think there is no one. So thank you again, Professor, for accepting our invitations and for your nice talk.
Yeah, I thank you all again, both you, the organizers, and all the participants.
Okay, I think Professor Babarslan wanted to say something.
Hello again, dear Professor Yıldıray Ozan. Thank you for your nice presentation. As always, thank you for your effort and support today. You are a valuable person to us. Thank you again.
Thank you very much. Yeah, for your nice words. Thanks a lot, Murat Hocam. Hope to see you some day, you know, really face to face.
We hope so.
Yeah. Okay.
I wish
Okay, now we have a 15 minutes break. After the breaks, there is one young researcher, Mücahit Meral. So let's take a break and then see you again.